So in the last video, I was just talking about, the half-life of carbon-14, which is 5,730 years. So two half-lives would be, if you found something where, the two half-lives have gone by, then that you could say that item is, that item is 11,460 years old. All right, but what about in between? I mean, there's that's there's several thousand years in there. What if you found something where it wasn't exactly two half lives that went by? Well, from the equation that I was mentioning before, um, you can use that. You can have some fraction of a half life go by, and you can figure out how much time has gone by. All right, so here's the next one. A certain isotope has a half-life of 1 day. So remember, half-lives can be days, it can be weeks, um, it could be months or years, seconds even. Some of them are seconds. Um, so a certain isotope has a half-life of 1 day. This means the amount of the isotope that remaining after 2 days. Okay, so after 1 day, it's going to be half, right? And then so it's half of a half. All right, so it would be 1/4. All right, that's the basic idea. So that's how it works, right? So 1/4. Right, and then of course 3 days, it would be half of that, so it would be one eighth, right? So it's basically one half to the power of however many half lives. So it's three half lives. It it would be to the power of eight, to the power of three. Sorry. So two to the to the uh, to the third power is that would be one eighth. Right? So that's how that's the way that this is the famous curve that we're talking about. Okay, so the radioactive isotope's decay rate is characteristic of each isotope. The rates described are described by the half life. The shorter the half life of a substance, the faster it disintegrates. In fact, that's just jumping a little bit ahead. That is actually one of the problems with nuclear power, right? We use uranium 235. We have to actually make the uranium. We have to manufacture the uranium 235 in what are called breeder reactors. Anyhow, when the uranium 235 decays, it decays into these kind of the atoms that are kind of in the middle of the periodic table, and some of them will have half lives in the thousands or even tens of thousands of years. I think there's one called There's one that's strontium, for example, um, that has a half life in the thousands of years. All right. So anyhow, so this is how it works. Let's say you started with 1 kilogram of some radioactive substance. After one half life, half of it is still radioactive. The other half is still there, but it's changed into another atom, another type of atom. After two half lives, then only 1/4 of the original amount is there, and so 3/4 of it have changed into whatever it becomes. It's usually we're talking about some stable atom, and then after so let's see. So this is one half life, two half lives, three half lives. So this would be um, 1/2. So one half, and you take the one half and you raise it to the third power. One half to the first power, one half to the second power, one half to the third power, and then one half to the fourth power, one half to the fifth power, and so on. All right. Generally, when you get to about 10 half lives, this is kind of a rule of thumb. When something so imagine, like, if you look at this curve, imagine 10 half lives, you virtually have almost no radioactive substance left. I mean, there's always some little bit of left, right? If this thing approaches zero, but after a while, it just becomes the same as the background radiation, and you just don't even have to worry about it anymore. All right, so this is what's called the transmutation of the elements. So this is the general thing. And so this is really good because this is an example of what happens in the upper atmosphere. So you have in the upper atmosphere, there's of course nitrogen 14. That's the normal nitrogen that is all around us. This is what most of our atmosphere is made of. Let's say you have an energetic neutron that comes along, right? The energetic neutron comes along, hits it's this thing is moving with a large amount of kinetic energy. This is, it's just a neutron, and it can pierce right into the nucleus, right? Because there's no charge, right? There's no repulsion for the nucleus, and so it can go right into the nucleus, and basically it'll join with the nitrogen. And then, actually, what happens is one of the neutrons will you see like the neutron doesn't really want to. It would become unstable. Like nitrogen 15 would be very, very unstable, and so it becomes another type of radioactive material, which is called carbon 14, plus it releases a hydrogen atom, right, or a proton, right? So it releases a proton, and when that happens, that you've created in the upper atmosphere, you've created nitrogen 14, and this doesn't happen. It's not like all nitrogen atoms. This is only a small fraction of the upper atmosphere, but it's a large enough fraction that we can actually measure the carbon 14 that exists in plants and in animals that eat the plants. So there's always, right now, there's carbon 14 in your body. It's, it is radioactive. It has a half-life of 5,730 years. And the thing that's really important about the carbon 14, again, is that this is nice about when you're considering living things, because the ratio of carbon 14 to carbon 12, the normal carbon that you find in a living creature, the ratio is pretty much constant while the creature, if a plant or animal is alive, and then when it dies, it's no longer bringing in nutrition from the outside world, and so the carbon 14 that was originally there begins to decay. I mean, it's still decaying inside, but it's not getting replenished with new carbon 14, right? Because it's the plant or animal is not consuming new more nutrition. All right, here's another one. This is uranium 238. So just keep in mind, these superscripts add up, right? So uranium 238 undergoes an alpha decay. So this is an alpha particle. This is just a helium nucleus. So this 4 plus the 234 has to go to the 238, and the 2 plus the 90. Now, suppose you didn't know that this was thorium. You just look up on the periodic table. Remember, you can just type into Google periodic table of the elements, and there is a nice active or interactive, I should say, periodic table. You can look up element 90, and this is its chemical symbol TH, which is thorium. Notice thorium is radioactive, of course, because it's above element 83, but the uranium 238 has become a new atom. This would be considered a daughter atom of uranium 238. Eventually, uranium 238 will become lead. All right, let's go on to the beta emission from a nucleus. You have no change in the mass because the electron is basically considered, it's so small compared to a proton or a neutron that there's no nucleon that's lost. But the atomic number increases by 1. So if an atom undergoes a beta decay, um, that atom becomes the next atom on the periodic table. Right? I don't know why it doesn't have the alpha decay. So well, this is alpha decay. So for an alpha decay, the atom becomes two steps down on the periodic table. For a gamma decay, there's no change at all. All that's going on with gamma is the nucleus is in a higher, it's in an excited state, and then when it emits a gamma particle, remember, is just a high the highest energy electromagnetic radiation. It's very, very dangerous type of radiation. But then all it does is the nucleus drops down in energy, right, from a heightened state to a lower state, but it doesn't change the nucleus. All right. So this is the artificial trend. We humans we can actually force this, right? We can take, for example, nitrogen and bombard it with a helium nucleus and form oxygen 17. So this is oxygen 17 is radioactive, and then from that, of course, there's also an energetic proton, which is just the reason they're putting the H there is that a proton is hydrogen, right? It's a hydrogen atom without an electron, right? So this is technically plus one, but as this thing flies off out into let's say you're on Earth or on some other planet, it's going to encounter a free electron somewhere, and that'll become a hydrogen atom. A neutral hydrogen atom. All right, let's see. Is that all I wanted to say? So elements 93 through 115 are actually synthetic. That is, humans actually created this stuff. You don't find element 93 through 115 in nature. So the last naturally occurring element is actually uranium. All right, so all this other stuff beyond it, neptunium and plutonium and stuff like that's all created. There's actually a very common one. I think it's 95 that is in almost in every house. It's called amerisonium, and it's used in smoke detectors, as a matter of fact. So that's one of the benefits of doing this. It's not all bomb making. All right, so when an element ejects an alpha particle, the resulting atom is reduced by 2. Right, so that's if it was a beta decay. The answer isn't here, but it goes up by 1. Maybe that'll be the next one. Yeah, there we go. I already anticipated that. All right, so if it ejects a beta particle, it increases by 1. So that should be B as well. Very nice. All right. Certain element emits 1 alpha particle and then produces 2 beta particles in succession. The atom, the result. So remember, the alpha, it drops by 2, and then 2 beta particles will bring it right back to where it was. So it would be 0. Right? It didn't. It underwent radioactive decay, but it didn't go anywhere. It didn't become a new atom. All right. So I was kind of talking about this already. For carbon dating, of course, we use carbon-14. Oh man, why? I think this should actually say 5,730 years. Let me check on that real quick. All right, so I quickly Googled this, and I remembered it correctly. So the half-life. We'll go with 5,730 years. I don't know why I don't know why it says 5,000. I think this is just a typo. Okay, so it's I'll try to correct that. Anyhow, we use this to that's not that much of a difference, but we use this to measure the age of things. Generally you can't go beyond like 10 half-lives or so. So